Hello, you all. This is Celso Batalha, Ashoten. And next week we are going to initiate the studies of evolution of stars. And as we tackle evolution of stars, I would like to initiate this browsing through the subject by reminding you of what we learned in chapter 5 as far as star formation is concerned. So stars are formed when gravity take over gas pressure, gas of what? Of pressure of what? Of molecules and in fact atoms that exist in the interstellar medium, and then gravity efficiently in some regions where the density is good enough, when the content, the gas content is good enough, so gravity starts to pull this gas in to the point that eventually a star is formed. Of course, there are so many other steps going on, but primarily gravity is able to overcome the repulsive gas pressure that exists in any gas inside a container, right? So you have pressure inside the tire of your car, um, and that is the result of all these little molecules colliding with the walls of the tire. And so think of a star as being some volume that is the walls of these volumes are being pushed outward by gas pressure. And gravity, which is the weight of the star, is the other force responsible for pulling it in. So if gravity is bigger, is more efficient, is stronger than the force resulting from gas pressure, then the star will contract. So eventually this gas will contract and eventually form a central star. So one of the learning goals of this chapter is to highlight that stellar evolution, the evolution of a star depends on the initial mass of the star, of the gas that is contracting to form the star. So more massive stars, let's say gas that are more massive than 8 times the solar mass, right? So these stars, this group of stars that are more massive than 8 times the solar mass, they will contract and evolve much faster than stars that are less massive. So stars that are less massive, they will end up their life cycle as what we call planetary nebula. Planetary nebula. In stars that are more massive than 8 solar masses, they will finalize their evolutionary stage as a neutron star or as a black hole. So you have these two different pathways depending on the initial mass of a star. So high mass are defined as those that are more than 8 solar mass. Low mass stars are those that are less. Okay. Now, the the Hertzsprung-Russell diagram is a diagram that relates in the y-axis in this vertical scale. It relates the amount of energy the star itself is putting out in the interstellar medium. So if you want to read this diagram properly, this y-axis is given in logarithmic scale. So 1 here represents 1 solar luminosity, which means if you take and if you compare the amount of energy all stars are sending out at a given time and compare that with the sun, so stars that emit as much energy as the sun are here listed as 1, and the y-axis is equivalent to 1. Now, stars that are 10 to the 1, which means 10 times as energetic as the sun is, are those that could be indicated in a diagram at that level. let's be a little bit extremist. So stars that are a million times as massive as the sun, as those that happen to be located right here. And in the horizontal scale is listed surface temperature. So the HR diagram or Hertzsprung-Russell diagram is a diagram that relates energy emitted or luminosity of the star and by its correspondent surface temperature. And the display goes that temperature diminishes from 50,000 or so degrees all the way to a few thousand degrees, 3,000 degrees. And in the Y scale, it goes from the subluminous component 10 to minus 4 of solar luminosity to those that are very luminous, more than a million times solar luminosity. So what astronomers did using the techniques that we learn in previous chapters, the chapters of stellar properties, I think was chapter number 10, that allows astronomers to measure not only distance to the stars, but also sizes, um, um, surface temperature, and other properties. Astronomers then collect all the possible information they have about the stars they could observe all in all its parameters, and they found that stars in general, 90% of the stars or more, they group themselves in this region, what which we call the main sequence. So the main sequence stars are the stars that are um, they are the majority of the stars in the galaxy. And we have another remaining 10% or so of the stars that are very luminous, but they are cold, and the stars that are very luminous, but they tend to be hot, and stars that are subluminous. Okay. So how the stars evolve? So the main sequence stars, as we saw in previous chapter, are stars that are undergoing fusion reactions in their very core. They are stars that are converting hydrogen, 4 atoms of hydrogen, into 1 atom of helium, and as a result of these fusion reactions, energy is being produced. And this energy escapes the core, and this energy is then used to be transferred to the gas that lies between the stellar surface and the core, and that energy is sufficient to warm up the interior part of the star and keep the star stable. So the star does not contract, the star does not expand, the star remains in the same size. And we call that hydrostatic equilibrium. Okay, so the core of the star is the region where the energy is produced, and the radiative shell is the region where that produced energy finds its way to the atmosphere and eventually escapes once it arrives the atmosphere. So, but what happened when the concentration of hydrogen in the core is finished? What happened when hydrogen is gone? So think about it. So what keeps the star shining for most of its lifetime is the existence of hydrogen in the very core. And 4 atoms of hydrogen are being fused, forming as a result 1 atom of helium plus energy. So what happened when all that hydrogen that is being fused into helium is gone? That's the main question. So when this happened, the star undergo changes, and these changes are the result of what we call pulse main sequence evolution. What happened after the star finalized, after the star ends its main sequence phase. So if the star is a low mass star, the core will slowly contract and heats up. And as a result of this slow contraction and heats up, the shell surrounding the core and is showing in this picture, the shell surrounding the core, this blue core, ignites in fusion reactions. The main point you should take out of this chapter is that when hydrogen is exhausted, the core contracts. The shell around the core produce fusion reactions in allowing hydrogen to be fused into helium, and but the net of energy produced in the core as a result of this heating up contraction plus the fusion reactions in the shell um, produces more energy than in previous stage when the star was in the main sequence. The main result is when the hydrogen in the core is exhausted and the core start contracting and fusion reactions are ignited in the shell, more energy coming out of the core, and that energy is then responsible for bringing the star to a stage of expansion. And the stellar surface expands and the atmosphere cools down. And the atmosphere cools down because the molecules comprising that make up the atmosphere, the molecules now increase their separation because of this expansion, and less collision takes place, the temperature drops. So as we studied in previous chapter, as the gas temperature drops, the color of the star, the dominant radiation the star produces, migrates from the optical range to the infrared, to the red part. So the star becomes an expanded, what we call red giant, red giant. Okay. So low mass star it's not there. So low mass star um, expands, becomes a red giant, and eventually the core in a flash, in a short amount of time, when the core is a helium core and it reaches 100 million Kelvin and the density is just right, that core ignites in fusion reactions, and it's called the triple alpha process. And as a result of that, carbon and oxygen is formed. So we have fusion reactions of hydrogen in the core in this further stage of stellar evolution, and then more energy is produced. The star becomes what we call an asymptotic giant brain star. Uh, so high mass star. So what's the situation with high mass star? So high mass stars are, in fact, before we go to high mass star, high mass star are stars that undergo a slightly different process from low mass star. So low mass star, once the core reach the temperature that is good enough to ignite fusion reactions of helium, forming consequently carbon and oxygen. When this phase is reached, and the core is a core of carbon, um, there is no more pressure originated from these overlying layers that can ignite further fusion reactions of the carbon, right? Because the star is a low mass, and think about mass as the quantity that gives rise to force, to weight. So the mass is not enough to ignite the fusion reactions in the core. But if the star is a high mass star, then the pressure is good, and fusion reactions will be ignited in the core once the carbon phase is completed, and then the star will undergo further fusion reactions in the core, further expansions, and the star becomes what we call a supergiant. Now, the end of evolution of these two groups of stars, one with less than 8 solar masses and another with more than 8 solar masses, is different. So stars that evolve and there were previously less than 8 solar masses, they ended up their lives as a white dwarf, a core of white dwarf that's pretty much carbon at very high temperature, and an expanding shell that's called planetary nebula. Whereas stars that originally were more than 8 solar masses, they evolve so that um, the final result of their evolution is what we call a core that is a neutron star, depends on uh, uh, the mass of that core, and an expanding shell, which is a supernova remnant. So supernova type 2 is this massive star that explodes and producing a lot of energy in its production. In fact, most of the heavy atoms we have in our environment came from these exploding stars. Supernova type 2 um, is is a type of explosion that is different from supernova type 1. Supernova type 1 is the resulting binary system of a low mass star that is being orbited by another low mass star. So, white dwarfs, which are the evolutionary end of a of the core of a low mass star. So white dwarfs cannot be more massive than 1.4 solar masses. But if the star is part of a binary system, transfer of material from the secondary towards the primary, which is the white dwarf, might bring the mass of the white dwarf to above that level, 1.4, bringing to a gargantuous crush of that core with enormous release of energy, which we call supernova type 1. So the importance of supernova type 1 is that since the mass of these stars are well known, 1.4 solar masses, and since the equivalent of mass is in energy is mc squared, so astronomers know the amount of luminosity of those exploding stars. So if astronomers observe an exploding supernova type 1, they know the distance to that star using inverse square law. And by doing so, astronomers use them to map out the universe basically and to establish a rule for the universe. So this chapter of low mass stars or evolutionary star pretty much covers this subject.